Here we have a statically indeterminate frame subjected to a concentrated load. We wish to analyze it using the force method. The frame has a degree of indeterminacy of 2, so we need to pick 2 of the reactions as redundant forces. Let's make the support reactions at B and C redundant. After removing the redundant forces, the frame is going to deform like this. We refer to the vertical displacement at B as delta B and call the vertical displacement at C delta C. Then we can write the compatibility equations this way. Now we need to calculate these displacements. Here is how we calculate delta B. Let me explain what we have here. Here we have the support reactions of the statically determinate frame. The dashed lines denote the member's bottom fiber. For member AD, bending moment equation is 50x minus 500. This is obtained by first cutting the member at a distance x from point A, then writing the moment equilibrium equation for the segment. Similarly, to get the bending moment equation for member BE, we cut the member at some distance x from point B, then we write the moment equilibrium equation for the segment. But since there is no force present at B or anywhere else on the member, bending moment in BE is 0. It should not be difficult to determine that the remaining members do not carry any bending moment either. So AD is the only load-carrying member in this statically determinate frame. Okay, now we need to calculate M star. To do so, we need to place a virtual unit load in the direction of the desired displacement at B. Since under the applied load only member AD has a non-zero moment, here, we only need to come up with the moment equation for AD. If we integrate M times M star, we get delta B. Since we already have determined bending moments due to the real loads, to calculate delta C, we just need to write the bending moment equation for member AD due to a virtual unit load placed at C. We then integrate M times M star to get delta C. We have 4 more displacements to calculate. First, let's determine delta BB. This is vertical displacement at B due to a vertical unit load applied at B. Since the unit load and the virtual unit load are applied at the same point and in the same direction, M and M star are going to be the same. Here are the non-zero moment equations, and here is delta BB. Delta CC, vertical displacement at C due to a unit load placed at C, can be calculated in the same manner. Here we have 3 members carrying a non-zero bending moment. Bending moment in BE and CF is 0. Next, we need to get delta CB. This is vertical displacement at C due to a vertical unit load placed at B. In this case, M and M star are not the same since the real load and the virtual load are applied at different locations. Here are non-zero M equations. Here are non-zero M star equations. And here is the integral of M star. Finally, we calculate delta BC, vertical displacement at B due to a vertical unit load at C. So what we refer to as M when calculating delta CB becomes M star here, and the M star we used for delta CB becomes M here. Not surprisingly, delta BC equals delta CB. Now we can write our compatibility equations and solve them for the redundant forces. The remaining unknown reaction forces, there are 3 of them, can now be calculated easily using the equilibrium equations.